Hello, it's Scott Manley here, and today I am at the Hat Creek Radio Observatory run by the SETI Institute. All these dishes around here are doing astronomy, or at least they will be doing astronomy when I'm not here with a radio source interfering.
So early in the year, I was invited by the SETI Institute to come up to see their Hat Creek radio telescope array. This is in a valley in Northern California near Mount Lassen, and when I looked at the map, I realised it would be a 4.5-hour drive. It would also be a 1.5-hour flight, so you know what I did. So it was the perfect use case for the aircraft, taking us up into the mountains in Northern California with some awesome views, including an early preview of the observatory. And yes, I did ask for permission before I went and flew this close. The valley is a radio quiet region, and of course the aircraft is emitting transponder signals, Wi-Fi, Bluetooth, and of course we passengers are carrying cell phones too. The observatory was first established in the 1950s by the University of California, Berkeley, with an 85-foot radio dish. This would eventually blow down in a windstorm, and a number of other telescopes were built and replaced over the years, but today it plays host to the Allen Telescope Array. That's a 42 antenna array, and it's the only one ever to be built with the specific intent of looking for extraterrestrial intelligence. The Allen, by the way, is Paul Allen, co-founder of Microsoft, billionaire. He funded a lot of different projects, including this one. He funded Burt Rutan's Spaceship One, which won the X Prize, Strato launch, and he also bought a MiG-29, which is now owned by Jared Isaacman. I, on the other hand, am of somewhat more meagre financial means and flew into Fall River Mills Airport in a little two-seater propeller plane. And there we were met by Dr Alex Pollak, who's the Director of Science and Operations at the observatory, so that he could actually drive us to the site itself. The observatory is situated in an enormously picturesque valley. This is an area that's famous for fly fishing. There's a whole bunch of cattle ranchers here. But the reason why the telescope is here is because the valley naturally provides a shield protecting it from electromagnetic radiation which might come from elsewhere. When you've built a radio telescope which is looking for alien technosignatures, the last thing you want is for it to be swamped by human technosignatures. And for this reason, before we could really start the tour, before I could get really close to the gear, we had to go over to one of the labs and I had to basically check all of my equipment to make sure that it wasn't emitting too much electromagnetic radiation because it could literally damage some of this gear. A cell phone sitting on the surface of the moon is a brighter radio source than almost anything in the sky.
Do my microphones actually make too much noise? Radio noise?
So even the spectrum analyzer is emitting noise, so that's why it goes into the shield.
Yes, you can shield it from itself.
Yeah, because if the door is open, you can actually pick up the spectrum analyzer.
Okay.
Measurements.
Okay.
And I'm going to say that while I definitely appreciated the importance of doing these kind of checks, I was approaching these particular tests with some reservations and concerns, primarily because the lab appeared to have been taken over by a swarm of wasps. But they seemed actually pretty chill, nobody managed to annoy them, and they pretty much minded their own business.
Is this system alive yet? Or has it been eaten by the wasps?
So can you close the door?
Okay.
The worst thing is you just do the baseline.
Okay. Make sure that...
How it should look like in there.
Yep.
So now you can see that's our baseline.
Yep.
And we already can see that's definitely something which already has Bluetooth, which leaks in from the outside. So who has a watch on, smartwatch?
I turned mine off.
Anything?
I turned mine off. Let me double check. Airplane mode over here.
It's airplane mode with Bluetooth disabled.
Yes, it is.
So if you don't, no, Wi-Fi is on, Bluetooth is on.
Oh.
So grayed out is not on.
Oh, I see.
Okay.
Proof. Okay. That's good to know.
We'll try this now.
And see if we get better. Yeah, I think we found something.
You found nothing?
But now it's,
Okay, where do I put them?
Anywhere in the room.
Okay, we're just going to sit them on the ground. Right? This is our thing here. Please turn off. Please stop making Bluetooth sounds. So they're like recording locally, so they hopefully won't be trying to wake up.
Pretty noisy, yeah. So you can see there's definitely some noise from them. We don't see Bluetooth yet. Okay. So a lot of that is, I would say, like clock signals, like the electronics of it, but we don't see any Bluetooth yet. But that looks pretty good, better than I thought. So,
better than you thought. Okay, so we can use those?
So I think that works, yeah.
Okay.
I would basically just keep them running, and that's it, yeah.
Okay, great. Let's go get them back out.
We're good to go.
Okay, oh, it goes down. Damn! Okay.
So let's take a look at stuff.
So I would say we start off with like an antenna.
Okay.
We go to one of those. So I switched off the receiver there, or the LNA, the low noise amplifier. So even after the test, if we missed something and if we go there, there's no risk of damaging something.
Yeah.
Only on that antenna. We should not go to the other antennas in case that.
Okay, so we could actually be
Bluetooth.
broadcasting too much noise.
Yeah, or too much signal in that
Right.
case. Yeah, because those are cryogenically cooled receivers. They are very sensitive. So if you imagine, if you would point them at the moon and there's like a cell phone on the moon, it would be the brightest signal in the universe.
Yeah.
And they can, for them, that's loud. So if you have a cell phone or something which transmits directly at a receiver, it would just break the amplifier, and then you have to repair them, and then it gets very expensive.
So is it the amplifiers upstream can just feed too much signal to the ones further down the chain?
Yeah, the first one are the ones which are the critical one.
Yeah.
And then the chain is designed that the rest would be fine. So the first thing when we get to here is there's a motion stop or an emergency stop.
Okay.
We push that one in because people use the array remotely. So they are sitting in Berkeley or in Oxford or in Penn State, and they remotely log in and start observations, and we don't want to have the antenna start moving while we're in there. Okay.
Okay, so it's basically a lot of space in here.
Yep. And then a very photogenic feed.
Ooh. It's like the ones we saw in the lab back there.
Yep.
Okay, so this is all voodoo, right? Because that's what RF is to me.
Exactly, that's black magic.
It's
that's
all
like,
black magic.
Yeah. We basically have the primary reflector and then the secondary reflector. The primary is 6 meters in diameter or 20 feet. And then it sort of reflects the signal to the secondary, and the secondary in front focuses it. They're collecting the signal and they focus everything on the phase center here. And that's where the feed sits. And that's a log periodic design, which is designed to make the transition from the waves in free space to the waves confined in coax cable. The cool thing with that design is you can actually measure how or where they're sensitive. So you could just take a ruler and measure the length of the spikes, and that's the quarter wavelength. So the lower frequencies are coupling in where the wavelength is bigger, where the spikes are longer, and the higher frequencies at the front here.
Okay.
So like a gigahertz is coupled in here, 10 gigahertz is coupled in on the front here. And that also means then that depending on what frequency you observe, you have to move the feed forward or backward. So you see it's on those rails here, and depending what frequency we observe, the entire feed moves to the front or back. So that's in the focus.
So to pause Alex's explanation for a moment, this is another example of the antenna, but this time it's not in the glass tube for the vacuum. And this is an example of what's called a log periodic antenna. The idea is that each of these spikes coming out the side resonates at a particular frequency depending upon its length. And by having such a range of lengths, the antenna is actually sensitive over a very wide range, something like 1 to 10 gigahertz. Now this is similar to the classic TV antenna lots of people my age remember. But this has essentially 4 of these antennae all arranged at angles to each other so that they can get horizontal and vertical polarization info. But that pyramid structure, that's designed to contain the amplifiers and their cooling dewar in such a way that the cables that loop around and come in the front have the shortest cable length before they get to the amplifiers. When the telescopes were originally built, they were sitting out in the air, but in 2012, they got some more funding from a guy called Franklin Antonio. Now, he was one of the founders of Qualcomm, and as such, he had a pretty good idea about building antenna. A number of upgrades were proposed and implemented with his advice and money, and part of that was to put the antenna inside these vacuum tubes.
The entire thing as well is in vacuum, so and cool down to 70 Kelvin. So minus.
Wait, this antenna?
This antenna, what you see here, is at 70 Kelvin currently.
Why is there no condensation on it?
Because it's in vacuum. So you have to sort of isolate it from the glass.
Okay.
So you can cool it down. If you imagine if there's moisture in there or anything, it would freeze on, and you would not be able to cool it down.
Yeah.
And the scary thing is with that glass, it's like 4 millimeter here, but it's only 0.5 millimeter on the
Yeah, if
front.
that shatters, that's going in our eyes, and you're the one with glasses, but I'm not.
Exactly. So we don't want to have anything. So that's why we usually have the cover on top of it.
Right, right. And that covers fine for operation, right?
Yeah. So it's transparent for the RF signals. It's tiny bit lossy, but it's more like to protect us.
Yeah. To protect us from this thing that looks like a death ray.
It really does.
It really could just shatter at the wrong moment.
Yeah. So after the signal is detected here, and in a cable, we just amplify it, and we use an optical laser and modulate it onto a fiber link, and then we send the analog signal into our signal processing room.
So the idea is that because you're sending the signal over long distances, the fiber optic is an optical signal which doesn't suffer from as much interference. It doesn't act like an antenna or anything.
Correct. So it's easy to send over long distances because the loss in a coax cable, especially at high frequencies, would be a lot. So you would need multiple amplifiers along the way, versus with the optical fiber link, if it's a kilometer or kind of a mile, that's no problem with it, even longer distances.
Do you have to account for, do they all have to have the same length because they're coming from known distances or whatever for your phased array thing?
Yeah, so they don't have to have all of the same length because we correct for it in digital then. So we sample them at the same time, and then we have ring buffers where we sort of offset it. We basically store the raw data then, and so we correct for the offset in length. But yes, that's a very important thing. On the old ones, they had delay lines where they had just coils of cables to make sure they have the same length.
Yeah, I'm just moving things around in here.
Yeah. And then, so we have 42 of those antennas right now, and 28 of those are equipped with that type of receiver and are used in our production backend for daily observations. And then we're building new prototype feeds right now to build out the rest of the array.
So actually, so this looks like it's on concrete piles.
Yeah.
You have to drill holes down for all of these?
Yes.
How deep do they go?
It depends on when we hit the lava rock. So they're about, I would say, about 30 feet or so, depending on when we hit the lava rock.
Yeah.
We had on the new telescope which we built, they actually hit a cavity last year, and it was pressurized, and a whole bloom of warm air came out with.
So this was the sedimentary or the lava rock?
Lava rock.
Okay.
Yeah.
Because we are surrounded by volcanoes and stuff like that. In fact, if I look all the way over here, that is Mount Shasta?
That's Lassen.
Oh, that's Lassen.
Yeah, so that's Lassen.
That's Lassen. And Shasta's somewhere over there?
Shasta is.
Oh, Shasta's sticking between those, right? Yeah. And that's potentially the most recent eruption. No, actually, yeah, Lassen
had one.
Yeah.
Yeah. And so you can see sort of there's all of the lava flows around the area.
Yeah.
So we are having that bit of.
Looking at this from the side, right? This is not pointing. Yeah, this looks like it's pointing directly at the horizon, but it's actually pointing 18 degrees up.
Yeah, that's correct. So they always look with the offset design. They sort of that's sort of the first question where people ask, oh, why are they looking at the ground? And it's no, they're actually kind of still pointing up.
But 18 degrees is the lowest they can point then?
About 16 degrees. So 18 is where we target, and the lowest they can do is 16 degrees.
Okay.
And then up to about 89 degrees, so they can get pretty close to.
Pretty close to zenith.
Yeah.
Right. How many of these dishes are out here?
So we have 42. They're they look like they're randomly distributed distributed, which they actually are. So if you look at kind of the distribution of those, it's sort of a Gaussian distribution.
Okay.
Because for imaging, you want to avoid having symmetries. If you have symmetries, you don't get more information. So
Right.
some of them are close together, some of them are further away, and that allows you sort of a very evenly sampled UV plane.
Right. But when you say randomly, you couldn't just randomly place them down because those might not actually be random enough. You had to actually come up
Yeah.
with a random thing that was actually mathematically random enough.
Yeah, yeah.
Yeah.
Look at there's a lot of even like PhD theses on like
how
how to place randomly enough, or what's the best distribution, what kind of random do you use. So there's a lot going into like how to place them.
Now here's a question then. We're adding another dish, you're saying?
Yeah.
How did that get added to the distribution to ensure it was random enough?
At that point, what we want is the distance. We want to have one which is further away.
Oh, okay, so this one's much further. Okay.
Yeah, so the plan is to have it completely down there about half a mile away, which gives you the resolution. So with an array, you combine them into one instrument. So if they're further away, you get a resolution. You don't get a sensitivity because you don't have the collecting area as one big one, but the distance gives you the resolution. And so with that one, we want to increase our resolution, and there were multiple spaces which we considered, and we did simulations of it, and I can show you like how they look like, the simulations, and based on what had the best coverage, we decided to place it down there. So all of the antennas, they're in groups, and you can see those node houses, what we call them, those metal huts, and that's where all of the fibers go and then are spliced together, and then one big like trunk line, one fiber cable with many fibers goes then into the signal processing room.
Okay.
That's also how they are cooled. So there's a big motor with a fan in it, and it blows the air through the ground, through the conduit, and we use the conduit in the ground to cool down the air, and then we pump cold air into the electronics in the antenna. But the thing which we discovered with like testing it, if you switch your iPhone off, it starts transmitting in Bluetooth. Because if someone steals your phone and they would switch it off
Find
my phone, that's the point where it then starts transmitting. And so having it on airplane mode with Bluetooth and Wi-Fi disabled is the best. If you start switching it off, we might have a problem.
I see. So again, don't actually turn your phones off, is what you're wanting to say.
Or disable the Find My Phone.
Yeah,
Part,
don't.
okay.
I would not recommend doing that.
So that's the antenna 43, which we have.
So this is the new antenna.
So that's the prototype antenna, which was in the Bay Area.
So this was a prototype that was built before the others,
Yes.
and then they've had this sitting around. You're like, well, let's set it up.
Let's bring it up, exactly, yeah. So it was in the Bay Area. They used that to develop the drive system and basically test the receivers and everything.
Yeah.
And so we brought it up a couple of months ago with a flatbed with police escort or CHP
Right, because it's more than 12 feet in diameter.
Yeah, it's about, 24 feet with that part, something like that.
So that's like take over the highway size.
Yeah.
Nice.
And so it's on a stand right now where we can work out if it's deformed or not, and then you can adjust the support structure on the back
So
to
you
make sure
like
that
dial in screws or whatever to tighten it in certain locations and correct for the shape.
Yep.
So while they're working on adding the original prototype dish to the array, they're also working on upgrading the antenna across the array. There's a new design called a dielectrically loaded quad-ridge flared horn. And this offers two major advantages. First of all, it expands the bandwidth now from 1 gigahertz up to 20 gigahertz. And secondly, it's a whole lot easier to manufacture. And so there's one dish on site which has been using this new antenna.
Oh, wow. So this is like totally different.
Yeah, so it's a quad-ridge feed horn, dielectrically loaded. And that one the feed horn itself goes from 1 to 20 gigahertz continuously. So it's very
this is a
broad.
wider band range, huh?
Yeah. And so from the front, it's hard to see now, but it looks more like a clover leaf, which has a dielectric spear in it.
Yeah.
And so that's the one for the third prototype. For the third prototype, we basically used the same one here.
Yeah.
But the problem there is because it's so close to the glass that the heat load is quite high because they're only a few millimeters to the glass.
Right.
and so cooling that one was very tough. From an electrical point of view, it outperforms the other one by a factor of 2, so it's twice as sensitive, but it was much more difficult to cool down. And so with the new cryostat, so when we replace the glass on it, that should fix that problem.
Yeah, so we can get a view from up here.
Yeah. Yeah, reliability and also just availability on parts. And there's like 15 years technology development in between. It doesn't make sense to build more of the log periodic one. They're far too unreliable and too complicated. So with something like that, it's far more simple. And so the other one, which is in the field, which is cooled down right now, it's pretty much the same, but it's in a cryostat, and it has a vacuum window and no glass anymore, so you don't really see it.
Cool.
So the radio dishes are the most distinctive feature that you would see if you're viewing the site from a distance, but they're really only one part of this observatory. All the signals that are collected, they are fed through a series of fiber optic cables to a central data processing system. As Alex mentioned, the radio signals are converted to an optical signal because if you send the radio signals down the coax, you're going to have much more loss and much more interference because you're running over longer distances. So it made much more sense to convert those to optical and then send them through the ground into the data processing center in the main building. And this is basically a server room with multiple racks of equipment. There's analog portions which will extract the relevant part of the frequency spectrum. Then there's digitizers that will convert those to numerical representation. And then, of course, there's a bunch of computers which will process this information and synthesize it. And, of course, storage arrays to make sure that this data is not just lost. Given the huge amount of progress made in computer technology over the last 15 years, it's not surprising to know that a lot of this hardware has been upgraded in recent years.
Okay.
Now this is really quiet compared to server rooms I've been in.
Hey, yeah, I think we're starting in front. It's after a while it definitely gets louder, but it's okay.
AirPods Pro noise cancelling really help.
But they're emitting. Can't have airports.
Oh,
no airports.
damn it!
You can get the classic foam.
Yeah?
Classic foam. No technology. But if you want to look for techno signatures, it's not good to
get a suffer.
Yeah, you have to reduce your own technology.
You should ask if you can get noise cancelling mode that turns Bluetooth off.
Yeah.
Until you put them back in the case.
Yeah.
There you go.
I'd be happy if iMessages would work if you're not on Wi-Fi.
Oh, okay, yeah.
That would work.
Again, I don't have any call there. You might have to find someone else. So these are all the fiber optic coming in?
Correct, yeah. So each antenna is one pair, so X and Y polarization.
Right.
And then they come in here, they go from the signal being on an optical fiber back on the signal being on a coax cable. We have what we call local oscillators. So they're used as very clean sine waves, and they're used to frequency shift the signal. So we up convert it, we filter it, and then we down convert it, and then we digitize it. And with that method, it allows us to do 4 independent frequency bands to observe those. So if you want to observe at a lower frequency and at a higher frequency at the same time, through the computer, you can just set it. Very similar to if you think of the old car radio, where you select a station, we can basically listen at 4 stations at the same time. Pretty much very similar.
What are the bandwidth on each of them? I guess that depends on what's on the other end, right?
Yeah. So for that one, so our sky frequency, if you're on the sky, we can go from about 1 gigahertz to 11 gigahertz. And on the digitizer side, we can digitize 4 times 700 megahertz. So in total, what's it, 2.8 gigahertz. And we sort of can distribute that.
700 megahertz band pass for each of these frequencies.
Correct. Okay. And then after that one, after we down converted it, filtered it, then we start digitizing it. And that's happening on all of those modules. Let's go around that side. And there's a lot of work going on right now.
Be careful not to stand in the hole.
It's open. But if you look at that one, so those are all of our digitizers. and they're programmed, they're all synchronized together, because if you want to combine the signals of the individual antennas, you need to make sure that they're digitized at the same time.
Yeah.
Otherwise you can't, if they move with respect, you can't really combine them. And each of those digitizer has two 100 gigabit output ports. So we're streaming out with around 4.2 terabits per second data. So every 2 seconds, a terabyte on raw data which comes out. And all of that goes into here, which right now we're wiring up. It's our digital signal processing switch. It's a 400 gig NVIDIA switch, which we just got a couple of weeks ago.
Yeah.
And so all of the data comes in from the digitizers, and then they all go out to the compute nodes.
Okay.
And the reason for that one, for having a big switch, is if you think about it, so a digitizer has all of the frequencies for one antenna.
Yeah.
But if we want to correlate them, so multiply the individual antennas, we need one frequency from all of the antennas. And so that's what is called a corner turn. So we have to reshuffle all of the packages that a GPU server only gets a certain amount of frequencies for all of the antenna. And so that's done with the big switch. And from there, we get it into our GPU servers, which are over there.
Right.
And so those ones are the one here. So they have big NVIDIA GPUs in them. We stream in with 2 times 100 gigabit, and we process the data in real time. And after the processing is done, we offload the data on storage. So that's one of our 2 storage rates. We have about 5 petabyte of spinning disk storage.
Yes.
And about 1.5 petabyte of tape storage. So we have a tape library, which we're setting up at the moment, where we can offload projects to.
For long-term storage.
Correct. And so after it's stored and you want to analyze it, basically what you do is you take the data off the disk, copy it into other GPU servers, and then you run your detection scripts on it.
Yeah.
But it sort of goes in parallel, because with a lot of the technology, what we have, a lot of the algorithms which we do, we can't really process it in real time.
Yeah.
So we might observe for 3 months, have a observing campaign which lasts 3 months, but then we spend half a year of analyzing the data, what we have on this, to look through if there's anything important in there.
Yeah.
And if we find something important, we start following up on those, re-observe, and
Cool the tapes or whatever.
narrow down on it.
So these are GPU servers and things?
Yep.
Right, so I didn't catch what class of GPU you've got in there.
So on those are the A5000.
Okay.
Right now for the production system, they're similar to the RTX 3090
Okay.
from the style. And that's like our current production system.
Yep.
But we have the new system which we are testing. And so they have the new RTX Blackwell, so the A6000 RTX Blackwell.
Yep.
Which I think 96 gigabyte of memory per card. And we have 4 cards in those, and we go in with 2 times 200 gigabit per side, so with 800 gigabits per second per server. So one of those servers replaces basically 4 of our current production system.
Right. And so we know it can run Doom. How many copies of Doom can it run?
Many.
Many copies.
Yeah.
Yeah.
And then so on top of that one, that's one of the GPU servers which we use to analyze the data then. And you can see they have like, 12 GPUs, I think, in there, and some very high-speed NVMe
So
rate
these are
cards.
just like commodity GPUs with the,
Yep.
display ports and everything still on there.
Yep.
But
But
those
we
are
don't-
all DisplayPort, not HDMI.
I think so. Whatever the industry,
Yeah.
all display. Yeah, you're right.
So, because HDMI, don't you have to pay a royalty or something?
Yeah. So those are all like data center GPUs.
Yeah.
We started off with gaming GPUs, and they work pretty well. But with our collaboration for NVIDIA now,
The ATA is a modern phased array telescope, which means it's using multiple antennas over a different range of locations. And by pairing them up and comparing the differences, you can derive higher resolution images than you would get. In the old days, you would have to build specific delays in and adjust those as the telescope moves. Nowadays, you can just brute force this on computers. These slides give you some of the actual numbers on the performance from this cluster. If you were having a hard time hearing what Alex was saying over the sound of the data center. These slides, incidentally, are from a GNU Radio presentation. GNU Radio started out back in 2001 as an open source project to develop software-defined radio technologies. And in 2020, it actually became part of the SETI Institute. Which really just shows how massively multidisciplinary the SETI Institute is. You have these people developing these technology projects, but also in parallel, you have the scientists looking at the real fundamentals of development of life and intelligence in the universe.
So, by the way, this says Sun Microsystems. Is that still Sun hardware, or is it just... says Sun Microsystems. Is this actually Sun hardware?
No,
yeah.
it's
You're
the
just
last
using the old
last rack, which is I replaced all of the racks, and that one was good, and I didn't replace that.
I just remember Sun when they were good.
But that's our housekeeping rack. We can go on the other side. That's where we get our internet connection. Where we have all of our network distribution for the observatory.
Okay, this is all your generic.
Yeah, all the generic
your firewalls.
Same thing as your your modem. We have like a 10 gigabit link coming in, internet. So I will definitely say we have the fastest internet in the area here. As a backup, we have a Starlink terminal.
Oh, you actually have a backlink, Starlink.
Yeah. So there's one on the roof, and if the fiber link goes out, the firewall automatically hands over to Starlink.
Yeah.
We had that a couple of months ago. I didn't even notice that the fiber link went out because I'm living on site, and my internet, it was a bit slower than usual, and I was like, okay, but not that it got me, that I realized the fiber link was out.
Yeah.
And what happened is someone with a shotgun was clay pigeon shooting, and they shot the fiber cable.
Oh my God. But ironically, Starlink has to turn off when they're going through your beam.
Yeah.
But
only for the direct to cell. So for the normal internet one, we don't really mind. They're above our frequency where we care. That one is our station clock. So if you think you want to observe somewhere, you need a reference frame.
Okay.
And our reference frame is time. So we have a very accurate clock, which is disciplined via GPS.
Okay.
And it gives us the long-term, so GPS gives us the long-term stability, and then the clock itself gives us the short-term stability.
Okay, so is that like an atomic clock or something else?
It's not an atomic clock yet, because those are very expensive.
Yeah.
They're the order of $500,000. I would like to have one, but I don't have the budget for it right now.
Curious Mark, you've got one running.
Yeah.
That you found in the garbage.
We could, There's the old Russian ones, which are really good, but you can't get spare parts anymore right now. So we use that one to discipline all of the digitizer. Okay. Then we have all of our local oscillators. So those are the ones which produce the sine wave. Yep.
And so the same frequencies go into every thing, right?
Yeah.
Okay.
And then weather station is very important for us. Like if there's high wind, we want to know where the wind comes from. Like same thing as an airport when you land your plane.
Right.
You want to know. Yeah.
So you have to figure out where to park the dishes, or figure out if they're pointing somewhere that will require.
So those dishes are not parking; they're actually windsocking. Okay. So they basically protect the receiver in the front end from the wind by just covering with the big back reflector of it. But that's usually, I think, if it's above 35 miles an hour, 45 miles an hour, the control system stops observation and takes over and then steers actively all of the antennas.
Okay, so you've got this like cool observation coming in, and you're watching that wind speed go up. You're
exactly.
Like, come on, I need my data.
Yeah. And at some point, just the control system takes over and that's it.
Okay, so how precise is this clock then? What is the...
It's a rubidium standard, which is sort of the next best you can get to a hydrogen meson.
Okay. But, okay.
In actual numbers, I would need to look at a data sheet.
Yeah. So, these things, I presume your frequency sources, you don't plug those things in manually. Those are remote controls, right? Yeah.
So they're all controlled via Ethernet.
Okay.
And then in the control system, if you start an observation, you just say, what frequency you want to observe, and the control system calculates at what frequency they have to generate a sine wave.
Right. So does that count for like motion of the Earth and stuff? Dopplers or
Not for that one. It's more just a translation between the frequencies.
okay.
So up conversion, down conversion, because we filter at 15.5 gigahertz. So whatever sky frequency you want to observe, let's say at 2 gigahertz, it has to end up at 15.5 gigahertz. And so that translation then
I see.
is done, because that's the filter and that one is fixed.
Right. So these aren't generating. Okay. These are generating the frequencies needed, not the frequencies you want.
Exactly, yeah. So they are used to shift the frequencies which we want.
Okay.
And then the other one is to down convert it then where we can digitize it.
Yeah.
So we just got a new board, which is a 64 gigasample digitizer. And that one would be able to just digitize the entire front end without any frequency conversion anymore.
Wow.
But the problem with that one is it has, for one antenna, then 400 gigabit. So you get many terabits per second. So it's of the order of 20 terabits
so
per second or
hard disks aren't
more.
keeping up.
So we need to keep up with the processing.
Right. I presume those disks there, are those SSDs now or spinning disks?
So it depends on, for the big storage, a spinning disk, like 16
so you still
terabyte,
have a lot of those.
20 terabyte. But for the one where if you want to capture raw data, those are NVMEs, which are rated as a RAID 0.
Yep.
So to add the write speed together.
Yeah. Right.
And so with
Just a bunch of disks.
Yeah, with the old ones, we get about 80 gigabits per second write speed, and with the new card, we get about 160 gigabit write speed, which is pretty fast.
That is pretty cool.
Yeah. And then that's our patch panel, where the different nodes come in.
Yep. So this is where they all come in from the outside?
Yes, yeah.
Nice.
And then we have more network distribution. So every place on the observatory ground, we have fibers everywhere. We have a white rabbit switch, which is a time distribution switch. So if you want to get the 10 megahertz and the 1 pulse per second from the station clock somewhere else, you can send that signal over optical fiber. And then you have an endpoint where you get a 10 megahertz out and the 1 pulse per second out again, which is disciplined by the station clock.
Okay. Cool. What's this? Oh,
so
this is the cooling?
that's our HVAC, yeah.
That's really old. Nice big chunky switch. I like it.
Yeah. So we get about 100 kilowatt of cooling power in here with the unit. We installed that 2-3 years ago, upgraded from one which was even older, and that one keeps everything cool in here. But the funny thing is you can tell when observation starts and the GPUs ramp up, the energy consumption goes up by quite a bit.
I'm sure.
So on average, we're at 60 kilowatt load.
On average.
Yeah.
Cool.
Okay.
In the past, people who wanted to use the telescopes would have to come out on site, and they would use this control room. Now, these days, it doesn't really get a lot of use because everybody can connect to the telescope remotely through the internet and perform all their observations without having to drive 5 hours to get here. The control room, of course, still exists. It has a nice view of the telescopes outside so you can watch them move, and some nice big screens on the wall with a dashboard showing you the performance of the various components around the cluster.
So we're in what we call the observer room.
Okay.
In the past, the observer actually came up here and was controlling the telescope from here. But nowadays, everything is remote. So people logging in via VPN and control the telescope remotely. So we have webcams or kind of cameras on site as well. So they can look and see if the antennas are moving or not. And an example is that's basically what you can see here. So that's like the view what the observer would see. They can move those antennas or the view around and look at individual antennas.
Yep.
And then that's what they usually see as well. So that's like a status monitor where we can see what the antennas are doing. So those are our 42 antennas right now. They're all running and they're all parked, like 0 degree in azimuth and 18 degree in elevation.
Yeah.
And then we see down here the sky frequencies, so at what frequencies they're observed right now, or where they would record the data if we start the recording. And that's the one which we can basically change with those local oscillators in there. So our radio channels, basically, if you think about it. The other part over here, there's a lot of housekeeping. So that tells us at what temperature the receivers are. So you can see there's one which is a bit higher. There's one which is at close to 300. Kelvin temperature, so that one is warm, and I know that, so I need to replace the cryo cooler on that one. We see the weather, we see like the power consumption of everything, we see temperatures, and so that tells me if there's any problem with the receiver system. And so it's basically, I just look at outliers in there if something shows problems. But that's sort of the main metadata.
Like this graph, it's got 200 and 0.
Yeah.
Wait, why is there a green one that's below 0?
So there, that's basically a readout, which is, so if you don't get data out, it's minus 99, so we know
Okay.
it's
breaking the laws of physics, so it must be broken.
Exactly. Yeah. And then you can see, so the main things like outlier where I can see there's a problem with a temperature sensor, if it spikes up.
Yeah.
And so those are kind of the indications what I'm looking for.
Turbo, wait, what's the turbo?
Turbo is the turbo pump for the cryo.
Okay.
For the vacuum system.
I was like,
so there's a
90,000 RPM is a lot.
Exactly. There's like a turbine in there which spins at 90,000 rounds per minute. And that one sort of, any molecule, anything which gets there is sort of like pushed to the back. And then there's a diaphragm pump which then sucks out whatever is
I'm actually impressed. It's like the range on that graph is 90,000 to 90,040.
Yeah.
Like, that is quite some level of precision
They're
for a
pretty
mechanical
stable.
device. Yeah.
Yeah. And so that's sort of an indication which we look at if there's a problem with a vacuum system.
Right. So if that graph has something that shoots off, it would be indication your pump bearing's going or something like that.
And then the main thing what I look at usually is the power consumption of the turbo pump.
Yeah.
And that tells me if it starts now drawing more power than usual, I know, okay, there's something.
So that red one might be in the borderline, or is that would be the next one?
There's definitely one which is a bit higher, which you can see here. And so we can look at it, 2H, that might be a diaphragm pump. So usually it's a diaphragm pump which goes, because then it doesn't produce a good backing pressure anymore. So we have our site UPS, our uninterrupted power supply. So the power which comes in from PG&E is rectified to DC and then backed up with this massive battery bank over here, and then it's inverted again to AC. And that power is fed to the antennas and to all of the computers.
Yeah.
So if there's a blip, if there's anything weird happening on our PG&E power, it's all filtered out.
Yeah.
So we're sort of generate our own three-phase 480 volt AC on site here to make sure that all of the expensive electronic is not being fried by a branch falling on a power line or something.
So this is doing the power conditioning, and this is doing a UPS.
So the UPS is that part here, and so we can look at the output right now. So we're drawing 54 kilowatt. And that's excluding the cooling, because the cooling is only on a backup generator.
All right, you don't care about that.
Yeah, so as long as it comes on the right side. So we had once that problem at the beginning of the year where the power failed in a way that took out the motor protection on the big cooling unit.
Yeah.
And it got handed over to the generator. The servers were fine because they were on the UPS, and then got handed over on the generator, and the cooling didn't go on anymore. It was offline for it. So within 4 hours, the temperature of the room went to about 160 degrees Fahrenheit. And I woke up in the morning and realized the power is out. So I came in and I already heard the server screaming and like knew, oh, there's clearly something.
They were just running their fans to try to cool down, bringing in hot air to cool down.
Yeah, so that was pretty bad.
That would not be fun being in that room.
Yeah, so at a point I went in, and at that point then I tried to switch off things, and the faster was just ripping out power cables.
You're just
flew through and just plugged everything out I could plug out. That was it.
Okay.
So those are the, if I can get it open.
Okay, so these are your backup cells.
Yeah, so those are the battery backup.
Oh, so these are like old school lead acid batteries.
Yeah.
Just like car batteries.
I wish I would like to do lithium ion ones, but the regulations, if you have lithium-ion ones, are far more strict than on those ones.
Well, I mean,
So-
it's staying still. You don't really care about the weight.
Yeah,
Right?
yeah. The problem is they have like a lifetime of about 5 years.
You can
So
swap
every
them
5
out.
years you have to swap them out. With the lithium-ion ones, they're like 15 years, 20 years.
Okay, I guess so.
So that's the nice thing, but the problem is, so that UPS is like 100 kilowatt, what it can last, and it's 15 years old, it shows aging, and we already ordered a new one with which has 225 kilowatt.
Yeah.
So we're doubling the capacity because with more instruments, more server at it, we're just needing more and more power all the time. So we are working on upgrading all of that. Because it's aging now, when they've done last time, they did the test of it, and so they switched it off. When they tried to switch it on, it failed 3 times and nearly dropped the load. And that was something which you don't want to have, because if the feeds go off, they're all cryogenically cooled. If they temperature cycle, there's a real risk that they would break.
Yeah.
And if they break, it gets very expensive. So at that point, they haven't been, when they get installed, for the last 15 years, they have not had a power outage. And we want to keep it at that.
You want to keep
So
it that way.
with all of the upgrades we want to do now, I need to figure a way, how can I replace that unit without powering them off? So that's the thing.
That would actually be, that could be an issue, actually. Turning these things off, they may not come back on in the same
Exactly.
state.
Yeah. And then on top of that one, we have our backup generator on the back here, which if the power goes out, there's in green a transfer switch,
Okay.
and that one switches then over to the generator. And that one is also, that's 38 years old, that generator.
So you get a big gas tank there, diesel tank?
Diesel tank. So we're in the process of getting a new one. So we get a 300 kilowatt diesel generator, so 3 times as big as that one.
So having spent a lot of time looking at all the other stuff, and more specifically staying out of the way of the killer wasps, we decided to return to the lab and see if they had decided to vacate the space.
This is like what the antenna looks like, actually.
Yeah.
In the...
So opened up. So we have like the feed horn in front, or the log period. We have the log periodic feed in front in the cryostat, and then that's our cryo cooler. It's a Stirling engine, which has helium in it, and then it's pretty much same thing as in a fridge.
Okay.
You have the cold side inside, and then you have the hot side out here, and we just have air blowing through through the heat exchanger here. Underneath here is our vacuum pump, so that's the turbo pump, which you've seen earlier, the data.
Yep.
So that one rotates at 90,000 rounds per minute. And then we have the diaphragm pump, which sort of creates the backing vacuum to the turbo pump.
Right, that's just like your base level vacuum. This is your proper vacuum.
Exactly.
Yeah.
And then we have our control board. So all of those boards are custom made for the receivers here. So they're designed in-house and then kind of assembled and tested and programmed here as well. So that's one. So that one will be converted into our new prototype feed, which is currently machined in Oxford. And then we have the other feed in the clean room area right now, and that one has a broken cryo cooler. So we will open that one up, take it apart, have a look if everything still works, and then replace the cryo cooler part, assemble it back on, make sure the vacuum is good, and then put it back on the antenna and cool it down.
So obviously this isn't pulling a vacuum right now because it's not running.
Yep.
So yeah, I'm just looking at the shape of this. I still don't get around how this thing works, but I guess I'm gonna have to watch some video about how these kind of antenna works. But the radio, the RF ends up going down this center feed horn, I guess you said?
So the connection is actually on front. So you can
Okay.
see here, that's where there's some coax cables where it's soldered.
Okay.
I don't think I have one here, but I think there should be one in the other lab which we can look at. But it's very tiny. It's very tiny connections.
Okay.
It's all soldered by hand. So the RF signal actually basically induces a current on the surface, and that one
on these
then,
side antennas,
Yeah.
and then it sort of basically excites this
Yeah.
front thing, which then goes down that,
coax in the middle.
right.
Yeah.
And that,
And
that
so-
horn shape then, I don't know.
Yeah, both of them are like 180 degrees So it's a differential input.
Okay.
And then it's both polarization, both linear polarization. So you have vertical and horizontal.
Right.
For those. But the problem with that one is like it's a 200 ohm, it's 200 ohm differential, and then to a 50 ohm coax cable. So it's, a lot of that is custom designed specifically for that instrument. And that was, if you imagine, it was kind of built, 2012 to 2018. And many years later, it's still one of the most broadband feeds in the world.
Wow.
So there's no other one anywhere else. And for the SETI research, it's important because we don't know at what frequency ETI would transmit, so we need to cover everything. So we need to design things which are very broadband.
Yeah, so you can't focus on the most efficient way to get a specific thing, because that typically doesn't cover the entire spectrum at the same efficiency. Yeah.
And then we have here, so a lot of the warm electronics, so afterwards. So those are the old amplifier modules. So the signal comes in, is amplified, filtered again, and each of the white ones is an amplifier. So there are many amplification stages in there. And so the problem with those ones is they're not broadband for the new upgrades, and you can't get the parts anymore, so they're obsolete. So we started redesigning the entire electronics, and I had a student from Germany here who did all of the RF design, and at the end we decided to make it modularized. So based on the function, rather than having everything in one box, we have it in small box. So we have amplifier stages, we have attenuator stages, power detection, and that allows us, if we need more gain, we just add another module in. If we don't need as much gain, we have one module less. If something breaks, we just replace one module rather than the entire unit. So it makes it much more efficient and easier to maintain.
The Antonio feed. So why does it say Antonio?
It's named after Franklin Antonio, who was a co-founder of Qualcomm, and he privately financed the upgrades for that feed, and now his endowment is funding the operation of the observatory as well. So thanks to him, everything you see here, everything we can work on is only possible because of him.
So Qualcomm, they know all about RF. Did he have like some hints and tips for you?
Yeah, he always said for SETI, it's not an astronomy thing, it's like a communication problem. So we have to approach it like from a communication point of view than from an astronomy point of view.
Yeah, I can imagine.
And so with that, I basically checked out all the important working parts of the Allen Telescope Array, the ATA at Hat Creek. But there is another radio telescope on site known as CHIME, the Canadian Hydrogen Intensity Mapping Experiment. Now, this is actually an outrigger for the main experiment. CHIME is a large static telescope. It's like 100 meters long, 20 meters wide, and it takes the form of like a half pipe. And it basically is scanning a huge part of the sky as the Earth rotates. It's looking at the 400 to 800 megahertz range, and what it's wanting to do is look at the distribution of hydrogen. So this telescope is supposed to be doing cosmology, looking at how hydrogen moves in the universe and how it is affected by, say, dark energy or dark matter. And the primary facility they built in Canada had basically 4 of these kind of half-dish setups. But what they also found was that this was a really good system for picking up fast radio bursts, very short radio burst events that would happen over a millisecond. And they were detecting a lot of these, but the problem was that they couldn't tell exactly where they were coming from. So they created a project to build 3 outrigger stations. There's one in Canada, one on the east coast of the US, and this one on the west coast. And when a fast radio burst happens, these are able to deliver the data that's required to triangulate the location on the sky.
Damn, you get like the murder hornets and the praying mantis? Onwards to CHIME.
So we are looking at CHIME FRB. So CHIME was an experiment for hydrogen mapping, and then they discovered they're very good at detecting those FRBs, they're like fast radio bursts. So those are very big explosions in the universe. They last only a few milliseconds. We know they're outside of our own galaxy, so they're very far away, very powerful, and we don't really know what generates them. So there are a few theories which so we have ideas of what it could be, but what we see isn't explained by that theory. So the leading theory is that it's a magnetar, like a spinning neutron star with a strong magnetic field, that could generate them. But again, we don't know yet exactly. So that theory doesn't explain
You don't have
everything.
a full mechanism for that.
Yeah.
Right?
So that theory doesn't explain everything what we see. So the main CHIME outrigger, or the main CHIME telescope, is up in Canada, and it's about like 8 times the size of what we have here. And then they build 3 outriggers. Another one up in Canada as a prototype, and then one here and one in West Virginia where the Green Bank telescope is. And so they use those, they all look at the same patch of sky. So the one in Green Bank is tilted more than the one here. And they look all over the same patch of sky. And with the time of arrival, we sort of can pinpoint the host galaxy of it. So we're trying to understand, does those galaxies have something in common? And so hopefully we learn more.
Hopefully we learn more. I mean,
Yeah.
yeah, so the whole thing with fast radio bursts is because they're so short, it has to be from a compact object, but they're enormously powerful, which makes it hard for compact objects, right? That's always...
It could be, you know, space battles, who knows?
Yeah, the universe does some very strange things to us.
Could be Star Wars just
Could be
happening.
Star Wars, yeah,
out there.
hyper-reactor on the Death Star, right?
Yeah, exactly.
But okay,
Very,
so-
very unlikely, but it could be.
Yeah, but this is it here. This is it's like a quarter pipe or whatever. Do people try skateboarding on this?
Not yet. I think you should try. It's a bit tricky. It's not a solid surface, so it's a mesh when we get to it. So it might be a bit tricky, but I definitely would encourage someone to try. I want to see that. So they have their own digitizers, they have their own GPU servers and then storage drives. And so what they do is they have a big ring buffer where they buffer the raw voltages. And if the CHIME main side finds an FRB, they trigger on it and they send a trigger signal to the outriggers and tell them to dump the voltages.
What they just did.
And then they take the voltages from the ring buffer, store it on disks, and then it's over the internet connection sent up to Canada into their data center.
So this is just basically running data, collecting data continuously, but it only dumps it out when the parent system detects something.
Correct. So the main thing they got from us is a 10 gig
Okay,
connection for the internet.
I see.
Yeah, and then they have their shielded room and the cooling
They have a
and
little
everything.
room over here. Okay.
Yeah, in the container, which you can look at.
It's a shipping container
Yeah.
with
is
a
sort of
lot
the-
of cables coming out of it.
And then we can have a look inside here.
Okay.
You can already hear the fans. So they have their own shielded room.
Yep.
Same thing as what we looked earlier for your microphone and everything.
Right.
To keep the interference inside.
Right.
That's basically where all of the antenna signals come in. And then they go into the digitizer. So those are the FPGA boards which digitize everything. From there they go over the network into the GPU servers, and then they dump the data onto the storage servers. So they have those big storage servers. And from there they then ship it out to Canada into the big data center.
When the things happen.
Yeah.
So yeah, it's all self-contained. Did they ship this container with all the hardware in it?
No, they actually build that shielded room on site.
Okay.
They bring the container, they build that custom-made in here, they test it to make sure that it's RFI tied, and then we install the equipment.
Right.
It's all done by basically postdoc students, researchers which come down here and develop or build the data, the hardware.
Hey. Oh yeah, so it's literally a separate room inside the container.
Yeah. And also isolated from it, so it doesn't have an electrical connection
Yeah.
to the container as well. And then you have those big inlet filters, those power filters, which make sure that
Yeah.
we're not contaminating anything outside. And then what goes in are the 2 fiber cables, which
Wait.
they have here.
Is it literally sitting on pieces of wood and duct tape?
Yep. Electrically isolated.
Great space applications.
So that was really all the important bits of the tour. Now, the telescope is actually technically open to the public on certain days, and the land is actually something that they can't close. People can come through. Of course, if you are going to go and visit in some form or another, please shut down all your devices. The purpose of the SETI Institute is to detect extraterrestrial intelligence, and it doesn't help that terrestrial intelligence just loves to scream in the electromagnetic spectrum. And let's be clear, this radio telescope is doing a lot more than simply pointing at other stars looking for signals from other worlds, other intelligences. The thing about the search for extraterrestrial intelligence is you only really want to look at the stars that have a good chance of hosting life. And that means you really want to understand the Drake equation. That's where you basically take the number of stars in the galaxy and you multiply it by the probability of life forming, multiply the probability of planets, etc., etc. There's all these parameters, all these multipliers that are in the Drake equation. And the SETI Institute, they have people that are working on trying to better understand all of these parameters. For example, there are people working on the asteroid impact hazard because that controls the chance that a civilization gets wiped out by asteroid impacts before they can start talking to the universe. And obviously that's a question I'm particularly interested in. And as for SETI, well, that is really one of the biggest questions we have. Are we alone in the universe? If we are, then it sure seems like a big waste of space. Hat Creek may indeed seem like it is a long way from anywhere else, but it is nothing compared to interplanetary or interstellar distances.
So I hope you all found that fascinating. Thanks to Alex, Steve, everyone involved at the SETI Institute for making this happen. It was fantastic. And yeah, I will get out of their hair so that they can start doing some science again. I'm Scott Manley. Fly safe.